and welcome to POW Science Module 2 Section 3, and this is Part 3, the Cross-Cutting Concepts. Our goals for this section of the course are to understand the intent of the 7 cross-cutting concepts, to distinguish between them, and to identify examples of the cross-cutting concepts in current curriculum and instruction. There are 2 main resources you want to have for this section. If you haven't downloaded these documents yet, please take a few minutes to do so. You'll want to have the PDF or hard copy of the framework available while you do your alignment, and the Cross-Cutting Concepts reference document I recommend you having out with you during this video. This would be a great time to pause and either print a copy or locate your copy of that reference document if you don't have it right now. The framework identified 7 cross-cutting concepts. The code we'll use for them in this course is the CCC. The cross-cutting concepts are the organizing concepts and ideas that we use to understand science. These are the big ideas that we see in all domains and in all topics. You can see both here and on the reference document, I've listed the page numbers in the framework so that you can find relevant sections. In this presentation, we'll go over each of the cross-cutting concepts. The reference document and framework go into detail about what the cross-cutting concepts look like in general and at different grade ranges. We'll walk through an example of how you might use these documents for alignment. The first cross-cutting concept is that of patterns. A summary statement for the cross-cutting concept of patterns is that observed patterns in nature guide organizations and classification and prompt questions about relationships and causes underlying them. The image I've chosen to use as an example here is the periodic table. I love this example because it's something that was created by scientists who had paid attention to patterns and used them to create something that we actually use to understand all kinds of things about the world around us. When you're looking at items within the NAEP, there are 2 key things that you might want to look for, and those are repetition and relationships. Many items that ask students to make sense of and reason about patterns will have a data chart, a table, or a diagram of some sort, but not all of them. The key feature will be that look at repetition and relationships. So in order to help you become more familiar with the reference document, I want to show you one page of the document here and do a quick walkthrough of how you might use it. As I mentioned in the last slide, we're looking at times when students are reasoning about a pattern to understand a phenomenon or answer a question, so that when you see an item like that, you might want to head to this page in the reference document, and then you'll be able to use this matrix for patterns. So let's think about a potential item you might be looking at. Let's imagine an item that presents a data table that has different cities with some information about each one, perhaps average temperature and rainfall at different times of the year, and latitude-longitude information. Perhaps this question asks students to look at one city in the chart that has an unknown and determine what the unknown is based on patterns seen in the data from the other cities. The material that I put into these reference documents is taken directly out of the appendix to the Next Generation Science Standards. And while we're not aligning directly to the NGSS, the feedback from the initial participants for this workshop was that this was a useful tool for alignment. So we can go to this matrix and look at these basic statements about what cross-cutting concepts would look like at different grade bands and look for some characteristics of a problem like our example problem for weather. So I'm going to zoom in on some elementary middle school level standards that look at weather might be appropriate in the 3 to 8 range somewhere. So if we look at these, is there a statement here that looks or sounds a little bit like what the question is asking students to do, that idea of identifying an unknown among cities? So I really like the cross-cutting concept statement in 6 to 8 where it says graphs, charts, and images can be used to identify patterns in data. The question we're looking at here really asks them to look at the chart and identify a pattern. And so I could use that statement for my alignment. I could also use that statement to go directly to the framework and to look at what the authors said. We're not going to walk through a sample like this for each cross-cutting concept because the structure of the document really remains constant for all subjects, but hopefully this example helps you to feel more comfortable with using the document and the example statements that we'll give during the presentation. So the second cross-cutting concept is cause and effect, mechanism and explanation. A summary statement for this one would be that events have causes, sometimes simple, sometimes multifaceted. Deciphering causal relationships and the mechanisms by which they are mediated is a major activity of science and engineering. Cause and effect can sometimes end up being a big umbrella. So much of science relies on the idea of cause and effect. Here are some things you can use as a jumping off point for your item alignment. Does the item draw on reasons? Does it have why statements? Does it have a before and after scenario? When you see those, it's a good indicator it might be the cross-cutting concept to start with. But just avoid that idea of making everything fit into this statement just because cause and effect is so integral to science. The third cross-cutting concept is scale, proportion, and quantity. A summary statement for this concept is that in considering phenomena, it's critical to recognize what's relevant at different size, time, and energy scales, and to recognize proportional relationships between different quantities as scales change. There are lots of times when we call on this in our instruction in order to better understand science. Some things to look for in an item would be measurement, estimation, and conversion. One thing to be careful of, though, remember we're looking at alignment where if the student answers an item correctly, it tells us something about their understanding. So some items might make reference to scale, proportion, or quantity as a part of a description or a setup, but if students don't need to use the information or reason about it anyway, then it's essentially background information. So when you're thinking of aligning an item to this, be sure to think about whether they need to use this concept or if it's just background information for the item. The fourth cross-cutting concept is system and system models. A system is an organized group of related objects or components. Models can be used for understanding and predicting the behavior of systems. There are many different items that require students to have some understanding of systems or system models. Some key features you might look for in an item is the presence of a subsystem, an interaction, or a closed and open system within a model. All of these are things that are sometimes included when we draw on this cross-cutting concept. But again, sometimes systems are being given just as background information for a question that's really drawing on a different concept. So be cautious. The fifth cross-cutting concept is energy and matter, flows, cycles, and conservation. Tracking energy and matter flows into, out of, and within systems helps one understand their system's behavior. Things to look for here are cycles, systems, interactions, and conservation of energy or matter. There'll be many questions that include energy and matter and don't really ask students to understand this concept, so be careful to look at the degree to which we want to see the movement of energy or matter, not just a static measurement. The sixth cross-cutting concept is structure and function. The way an object is shaped or structured determines many of its properties and functions. Often biology courses have an entire chapter or unit just about structure and function, but this concept is integral to all areas of science. Think of the structural changes to atoms between elements and the impact that has on the properties of the substance. Or think about how the structure of something like the bridge shown here determines its function. Things to look at are things like object shape. If an item asks students to think about the shape of an object or item in answering a question, it may be drawing on this concept. Also, look at questions that ask students to design or select a structure. Finally, when an item looks at overall pieces versus component pieces, we're sometimes really looking at structure and function. For example, think of the way different component pieces of the cell perform their jobs based on their structure. Finally, the seventh cross-cutting concept is stability and change. For both designed and natural systems, conditions that affect stability and factors that control rates of change are critical elements to consider and understand. Two things to think about when looking at items for this. First, this is a special case of cause and effect. So if you're looking at an item that you think is cause and effect, you may want to ask yourself whether the cause and effect you're seeing is one of stability and change. For example, in an ecological system, the introduction of a new species will initially cause a change, and over time we often see stability return to the system as the animals adjust to the presence of the new species. This is an example of cause and effect, but it fits into the very specific category of stability and change. Another thing to look for is questions that prompt students to look at order and disorder. Sometimes these items are drawing on student understanding of stability and change.